Hello, and welcome to this week's Machine Learning Optimized Systems seminar. Seminar brought to you virtually in cooperation with the University of Wisconsin-Madison, Microsoft Research, and of course, COVID-19. So thank you for joining us today once again, and I hope everyone's out there and doing well and staying healthy. Today we have a great privilege of welcoming Professor Shiv Venkataraman with us to our seminar. He's an assistant professor at the University of Wisconsin, and he's been doing some fascinating work at the blend or the boundary of systems and machine learning for some time now. And he's going to tell us today a bit about both perspectives on that, both systems for ML and how ML can help systems. Shiv is also a fantastic teacher, so if you don't like his research, I think at least you'll like his educational style. Thank you, Shiv. I'll hand it over to you now. One thing I will say about how we'll operate here is if you have a question, please put it in the Q&A. A few of us will be monitoring that, and we'll occasionally interrupt Shiv to ask him a question. Shiv, if you could remember to once in a while kind of check with us so that we don't feel so impolite just running into your text. So after you.
All right. Thanks, Ramsey, for the introduction, and thanks also to Microsoft Research for helping organize this seminar. I'm Shiv Venkataraman, and today I'm going to be talking to you about sort of research at the intersection of systems and machine learning, and what are some opportunities and challenges for doing symbiotic research. I hope my audio is loud and clear. I'm assuming if nobody says anything, it is. Okay. All right, so let's get started. So I think it's good to start by talking about what do I mean when I say systems, in case you're new and you're joining out here, right? So systems, I think, is sort of a foundational part of what we are using, computing that we're using every day. This includes the operating system that you're probably running on right now, databases that are like storing your information, and file systems that are storing all of your data. And of course, computer networks that let us connect to this Zoom session and sort of keep the world running even when we cannot do things in person. Also, a fun fact, there are no very good pictures that actually represent systems themselves other than things with boxes and arrows and things like that. So I use textbooks instead, which have very nice covers in this case. On the a recent development, in case you haven't noticed, is this advent of machine learning, which is either the artificial replacement of a human brain or a bunch of magic that we don't understand what's going on, or somewhere in the middle between those two extremes. And this advent of machine learning has created a lot of interest and opportunity for systems research. So today what I'm going to do in this talk is try and talk a little bit about these two complementary sort of areas that have popped up as a result of this advent of like machine learning algorithms. These are using machine learning to improve systems, or for short, you can call it ML for systems. And the second part is about designing systems that can actually improve machine learning, or systems for ML. Now, you might be wondering what is different about these two topics, or what are some examples of like problems that would fall under the left bucket or problems that would fall under the right bucket, right? So problems that fall under the left bucket include things like predicting the performance of your application, right? This is a long-standing problem of like, I'm going to run a query, I'm going to run a MapReduce job, I'm going to run something, and how long is this going to take, right? But it also spans from more than just prediction to, for example, performance tuning, where you want to optimize your system so that it will actually run really well given a particular workload or given a particular hardware resource, right? And the natural extension of that being that you want to use machine learning to answer questions like, how many machines should I allocate for this workload that I'm running? Or what are some of the, should I use like GPUs to do this? Should I use CPUs to do this? Or ask such complex questions like that, right? So these are a few examples of what one can do using machine learning that will actually improve systems performance, either on the performance axis or on the cost or resource efficiency axis. Now, whenever there's a research problem in ML for systems, some of the questions that I think are worthwhile asking are, This first question, which starts from, do we really need a machine learning model, right? So unlike a lot of other domains that machine learning is used for example, to understand images or to understand paragraphs of text, systems are things that we built. Groups of programmers over many years have come up with design documents and specifications and like source code, test cases, benchmarks, and all of this thing to put together a system, right? So it is something that we created. And so there's a question of, do we actually need a machine learning model to tune this or to predict this behavior? And if so, how complex a machine learning model do we need? And if we are going to use machine learning, then some of the interesting questions to ask are, how expensive is it? And if you are going to use a lot of cycles to run machine learning to tune your system, right? Do you get something that is accurate, reliable, and maybe even explainable to say that this is why your system is slow, or this is why your system can be accelerated, and so on, right? So these are some goals or aspirations that we have when we consider ML for systems. Now, on the other hand, if you consider systems for ML, the set of problems that we might consider might look something a little bit different. Some common concerns here include, for example, things like designing programming models that make it easier for machine learning users or developers to express programs that can then go ahead and like learn these complex models. It could also include traditional systems concerns, like, for example, scaling a machine learning program that's been expressed to run on many machines or to run on really large data sets and so on. And of course, the last one comes as a result of scaling is that you don't necessarily have one machine learning model being trained. You have a bunch of them being trained at the same time. So how do you like share resources, or how do you do scheduling of like various tasks that come up? Now, if you think about programming models, scheduling, and scaling, these are all traditional systems concerns, one could say, right? These have been solved for other domains, like, for example, you're writing a analytics query, let's say it could be SQL or something like that, or it could be any other kind of like workload that you're running. So a key question to ask when you're designing systems for machine learning, or when you're doing a research project, I think, is what is different now that we have these machine learning workloads, right? So what should be different in my programming model, or what should be different in my scheduler, just because I'm dealing with machine learning workloads, right? And a follow-on question to that is probably, how is this design actually going to handle the range of models and hardware that machine learning workloads are going to be run on? So I think this is particularly a pressing concern, because if you look at how many new models are being proposed every day or every week in the area of machine learning, this is a fast growing number. And so in some sense, the question is, how do these systems sort of like keep up or keep track of what is going on in machine learning? Right? So I've so far introduced this as sort of a Boolean left versus right, ML for systems or systems for ML, right? And in the last part of the talk, I'll talk a little bit about like how this might not necessarily be a strong separation, and how there's actually like overlapping problems that sort of span across both of these areas. All right, so that is a quick outline of my talk. So now I'll go on to the first part where I'll talk about ML for systems, and specifically a case study that we did with respect to database tuning. So this is work that was published this year at Hot Storage 2020, and by looking at the name of the venue, you could guess that this is work in progress. So these are some early results that we have that I'm hoping to sort of like kindle more discussion about. And the main question that we were studying here is this question of like tuning the performance, but specifically of like database or like storage systems that are deployed in many settings, right? And the problem here is something very simple, which is that let's say you have a distributed database like Apache Cassandra, right? You can download it and you can start executing Cassandra and run its configuration and get it running. And what you would have is like some set of default configuration that ships with the software, right? So in this case, that might mean that a number of different variables like the commit log sync period and the concurrent reads and concurrent writes are all set to some values. And these values are what the developers think are maybe good values to have for these things. Now, the performance tuning process is basically looking at this default configuration file and a set of workloads that you want to run Cassandra on, right? And then come up and say, this is how these configuration knobs should change in order for the performance to be optimal or for it to be better than what the default configuration is giving. Right? So in this case, for example, you might change the number of concurrent reads from 32 to 128 or 32 to 64 or for concurrent writes and so on and so forth. Now, this has been a long-standing kind of like challenge is like, how do you go from this default configuration to a configuration that works well for your workload or for your hardware, right? And typically, this is in the domain of like database administrators or experts who can come in and set these values. Right? Now, a recent trend has been to try and like automate this process and specifically automate this process using machine learning, right? There are a number of recent papers that have been published related to this. A couple of examples are OtterTune from Sigma 2017, and also an RL-based framework called CDB-Tune from Sigma 2019. The range of these papers can be summarized as something at a very high level like this, right? Which is that you have a list of like tunable knobs and some workloads that you're interested in, right? And the first initial step is to try and like sort of understand what the system's performance characteristics are by running a bunch of these configurations and evaluating them and storing some of this performance data that you have to either like train a machine learning model or to put it in like a knowledge base or something like that, right? So we call this as an offline profiling phase or a training phase where you're training this machine learning model by generating a bunch of different configs and looking at the performance related to those configs. Now, once you've trained such a model, the online tuning phase is that given a new workload or some subset of knobs, right, you would ask the model saying, oh, please, can you tell me what are the optimal knobs for this workload? And the model will give you some prediction that you will then put into your system and then check how well it is doing. Right? So this is how we are actually going to use the database tuner once we have like built it. So given this kind of setting, the first question that we wanted to kind of understand in this work was that how many knobs do we actually need to tune for a database in order to achieve good performance? Right? So the good is inside quotes out there because one of the first things is to define what do we mean by good performance. Right? So we looked at this problem to kind of like try and like reach this question of like, if you're going to use a machine learning model to do this, the complexity of the model and like the characteristics of the model, of course, depend on the number of knobs that you have and the search space that you're kind of like looking into, right? So we wanted to understand this question first, which is that how many knobs do we actually need and how do these systems behave when you're actually doing this kind of like performance tuning? So the methodology that we used in the study was something as follows, right? So we picked a large set of knobs, around 30 or so knobs in a bunch of different systems like Cassandra and Postgres. I'll mostly be presenting results from Cassandra. And the first step that we did was we generated what we call as a ground truth data set, right? So here we just like generated a large number of configurations, right? We ran the system on these configurations and we just saved all of the performance data that we got and put it into this large data set. So this is in some sense a brute force tuning methodology in some sense because we just tried out really large configuration number of configuration values just to kind of know what is the best case performance possible. Now, following that, we did this exercise of saying, if we didn't actually tune all of these knobs, right? If we were to tune a subset of these knobs, how is the system going to behave? Now, in order to intelligently tune a subset of these knobs, we tried to do an exercise of trying to identify the most important knobs and then rank them by the order of their importance, right? So if there are 30 or so knobs that we started with, are there what is sort of how important are each of these knobs in order to get optimal performance, right? And lastly, we then checked if I only tuned the top K knobs that the previous step identified, right? What is sort of the performance that I get, and how does that compare with the ground truth data set that we had in the first case, right? So now I'll just go into a little bit more detail about how do we identify these most important performance knobs. So at a high level, what it looks like is that we have a bunch of these different knob values, and we are running these experiments and measuring the performance. So in this case, latency or throughput, right? And we're just collecting this data as we keep going along. So our input to identifying important knobs is something which looks something like this, which is that you have a bunch of different like configuration possibilities, and you have some corresponding performance values that you observe as a result of that. We train a very simple regression model, right? Using these as the features, the knobs values as the features, and the performance as the outcome. This regression model is part of a random forest, and we specifically chose a random forest because it's useful for giving us these probabilities or these importance values for which knobs are important for explaining the performance that we actually see. Right. And so the output of this random forest is to tell us something like this is the relative importance rankings of these ranks, right? With a higher value meaning that it's more important and a smaller value meaning it's less important. Right? So this is sort of the overall setup that we are at. And now we ran this on a number of different workloads. I'm going to present a subset of results, and there are, of course, more results in the paper, and I'll be happy to chat more as well about it. So let's first consider Cassandra running with the Yahoo Cloud Serving Benchmark, YCSB. YCSB-A in this case, which has like 50% reads and 50% writes. So we plotted the relative importance of knobs, and I think this is like the top 10 or top 15 knobs that are present in the system. And we see something which is kind of very interesting here. So what we actually observed was that these top 5 knobs that I've circled out there, they actually have the most impact, and all of the other knobs have very minimal impact on the performance of the system. Right? We also did a little bit of like background research into figuring out what do these knobs represent. These knobs, for example, represent things like how many threads are being used to serve read operations at the same time. What is the number of what is the size of the mem table and when the mem table should be flushed to disk. So this is some in-memory state that Cassandra is keeping. And do you flush it very often or do you flush it like periodically, right? And so these handful of knobs seem to affect the performance the most. But now the second question is, OK, so now we're making this claim that only these 5 knobs affect performance. Is that actually true, right? So if I only tune these 5 knobs, will I actually get good performance, right? So we tried to do that by comparing what would happen if we only tune these 5 knobs as opposed to tuning all of the 30 knobs that we had considered as a part of this ground truth data set. And what we actually found was that we were able to get more than 99% of the peak performance by just tuning these 5 knobs, both in terms of throughput and in terms of read and write latency, right? So in some sense, just tuning these 5 knobs gets us like almost all of the way there, as you would have gotten if you tuned these like really large set of knobs as well, right? So in combination, what these 2 results tell us is that the search space that we need to consider is really not that large, right? And we actually can consider a much smaller search space and get really good enough results, and thereby making the problem a lot more simpler than one would have expected. Any questions or comments so far? I realize that Ramsey said I should check, and I do the same thing with my students, so this is a good reminder to do that.
Yeah, thanks, Shiv. I think a couple points. One was, maybe the shorter version of this, how do you propose addressing issues of performance tuning when the distribution is constantly changing, of your observations or something like that?
Yeah, no, this is a very good question. I think the other kind of like limitation or assumption that's being made here is that you're tuning for a particular mix of like workloads, right? Or mix of like distribution of like queries or distribution of keys and so on, right? And if that key distribution changes, the assumption is that you're going to redo this tuning process, right? So when I first brought up this question of is it cheap to use machine learning for systems, that's one of the reasons it's important for it to be kind of cheap and fast, because you can then do a retraining or like an update your model based on the new distribution that you're seeing, right? So that is a second, I would say a second challenge once you have a good static tuner in some sense. Yeah.
Great. And then how do you deal with correlation between the parameters?
Yeah, so this is so there are parameters which probably are correlated in the sense that if you change one parameter, then or if one parameter's value gets affected, then the other parameter's value gets correspondingly affected, right? This is something that the modeling engine, so whatever is the machine learning model that you're using, is probably trying to handle, right? So in some sense, in the classic machine learning problem, if you have too many features compared to how much data that you have, right, there are many features which are probably correlated with each other, right? So that could also happen in this case. As with most machine learning problems, the answer is to have more data, right? So that you can detect these correlations during the learning process and like account for them. And so there is also always this constant tension between how much data do you need and how many features do you use as a result of it. Yeah.
Great. And I think people are then asking specifically about how much data do you actually need for these approaches to work, and then what were the number of samples taken when training the random forest?
Yeah, so this is a good question. So for training this random forest, we trained the random forest on this like ground truth data set that we considered, right? So I think we collected around like 10,000 samples or so, and each of these were like 5-minute experiments that were run on Cloud Lab, right? And then we used like a sampling scheme to sort of like collect these 10,000 data points and do that, right? And then all of these 10,000 points go into this like into this random forest method to come up with the most important knobs. Right? Yeah.
Great. Why don't we just continue for now? We might have a few more questions as we go.
Great. Sounds good. So where we left off was this point that tuning 5 knobs gets us almost all of the performance. Now, you might ask, oh, is this something specific to Cassandra? Maybe Cassandra is kind of strange. It has like, a lot of like flags which don't really matter. So we repeated this also with Postgres, very popular SQL engine, right? And we found kind of similar results with Postgres as well, where there were a handful of flags. So in this case, like 4 flags that was able to explain almost all of the performance variance that you would have as you did tuning. But there's another interesting result that came up when we were looking at the Postgres results, which is that if you look at the 2 of the top 4 flags that are shown, or top 4 knobs that are shown in the figure, one of them is fsync and the other one is WAL_sync_ method. So in case you haven't guessed what these flags do, fsync controls whether Postgres calls a flush on the file system or not, anytime it wants to kind of like push something to the file system. And the WAL_sync method is correspondingly to for the write-ahead log, what is sort of the synchronization method it should be using. Now, adjusting these flags obviously impacts performance, which is what our figure here is telling us. But it does more than that. It also impacts the reliability that we would get in case of like failure of like Postgres, in case it crashes, or in case there are disk failures or operating system crashes or things like that. Right? So one of the other limitations of a number of like tuning methods that we have seen so far is that there are actually constraints which are more than performance that we care about when we, let's say, talk about a database system or when we talk about a file system. And capturing all of these constraints is not really trivial right now, right? Because we want to say something like, oh, I don't want to actually lose data, but I want to like get the maximum performance possible without losing any data, right? And that is much more harder to express than just saying that I want my database to run as fast as possible. So this was a short tour through a set of issues that comes up when you try to do database tuning, and especially when you try to use machine learning to do database tuning, right? And it's kind of interesting to revisit these 3 questions that I put up earlier in the context of this early work that we've done so far, right? And so if you look at like how complex a machine learning model do we need to actually do this tuning, if you are only going to tune a few knobs, then you probably don't need a very complex model, right? But the challenge there is how are we going to identify this, right? These subset of knobs, and is there are there like, smart methods that will help us like identify this subset of knobs, right? And this is work that we're currently, investigating, and there are many different kind of like ways in which we can do this, right? And for the second question about like, how expensive it is or how reliable it is, clearly, if you're tuning a very large set of knobs, it is quite expensive to collect these like 10,000 or so samples, and each of those experiments run for like 5 minutes. That's a large number of like core hours that are being used up, right? So any method that brings it down to a much fewer set of knobs will make it like cheaper, which is good. But on the other hand, there's also a lot of open questions in terms of like reliability, specifically in terms of like how do we come up with a richer set of like specifications that can make sure that the database tuner is going to give us like answers that don't like sacrifice reliability or that don't sacrifice explainability, and so on, right? So some directions and also some open challenges that remain to be done in the context of machine learning for systems, especially when looking at this performance tuning angle. So now I'm going to switch gears a little bit, right? And I'm going to talk about systems for machine learning and sort of some of the problems that come up in that space. So if there are any final questions about this part of the talk, I'd be happy to take that now before I kind of switch gears.
Yeah, there are a few questions, Shiv. Kind of, here's a simple one. Random forests are generally thought to be slow. So is that, seems like okay, but I don't know if you have thoughts on
I don't know if random forests are thought to be slow. That's kind of news to me. I think random forests are, in this case especially, we were training it on like around 10,000 data points. So the speed was not much of an issue for us, right? I guess they might get slower if you have a lot more data points, right? So but there are other methods which I guess we could try out as well.
And I guess there was a question, are you using permutation importance or MDI for feature importance?
I am not sure about that. I will have to check up on that. Yeah,
chime in on that and with a little more detail.
Yeah,
I don't have more detail on the question.
Okay, yeah, but feel free to contact me after the talk. I mean, yeah, or if you can stay back after the talk and.
Yeah, I will. Even though it's not me. But maybe I don't know if Andreas wants to chime in on that. But the last question here was, are important knobs in any of these DB systems related? Like, can you learn something? Is learning in one give you any insight into learning in another?
So this is a great question. So this is something that we don't have a very strong answer for as of yet, right? So it's clear that there is some knobs which are related to especially persistence and how often do you use the disk or how much memory do you allocate for certain regions, right? For example, shared buffers in Postgres and mem table size in Cassandra that are kind of analogous to each other, right? So there's some interesting questions about, can you actually like, sort of see which are these knobs? I mean, when you run benchmarks or when you run like profiling, can you actually see which of these flags are actually controlling, these performance critical or these performance sensitive regions of the execution, right? I think it's very interesting work to do in the future. So we do see some patterns, but nothing stronger than that right now. Yeah.
Great. There are some more questions, but I think we should probably move on and then maybe get to things at the end.
Sure. Yeah. Thanks a lot. Thanks for the questions. Okay. So now I'm going to switch gears a little bit and talk about some of our work in systems for machine learning. And here I'm going to use a different kind of application as a case study, with the application being cluster scheduling. Right? So cluster scheduling is a well-studied problem in like a collection of like when you have a collection of machines, either it's inside a supercomputer, it's inside a data center, right? In all of these cases, we have a number of users who are kind of like submitting jobs, right? And we want to run them on some set of like shared resources, right? Now, in the context of machine learning, this boils down to the fact that a number of users are training machine learning models, right? As shown on the left here. And they're trying to submit these training jobs to this like big shared GPU cluster, right? Or a cluster fitted with other accelerators. We use GPU as a stand-in for accelerators. And there's a cluster scheduler that sits in the middle and arbitrates how these jobs are going to get access to these resources. Right? So as I said before, one of the primary questions to ask in every systems for ML research project is what is different now, right? So we've built cluster schedulers for running MapReduce workloads, or we've built cluster schedulers for running like SQL workloads or things like that, right? So what are some of the differences when you talk about machine learning workloads? So one of the primary differences is that machine learning workloads, in distributed machine learning workloads, they have this property of requiring gang scheduling, which just means that if I have a TensorFlow job and it requires 4 GPUs, it wants all of those 4 GPUs at the same time. So you can't give it like 1 GPU at a time, because to make progress, it requires all of these 4 workers available at the same time. There's a second challenge which comes more from the hardware side, which is that a number of these accelerators are monolithic resources, in the sense that the accelerators that are currently at least deployed in data centers, there is no way for you to run more than one workload at the same time on the accelerator. Right? So if I gave this GPU to this TensorFlow job, then it's not possible for me to give the same GPU to a PyTorch job at the same time. Right? So sharing is kind of more tricky because you're making these decisions on monolithic resources. The last thing I want to say is about locality, which is that these different workers in a machine learning job communicate with each other, and they communicate at a very fine granularity, often at the end of every iteration, which is order of like hundreds of milliseconds or so. And thus locality, or like putting all of these workers close to each other with close defined in terms of network topology, is important for performance. So cluster schedulers for machine learning workloads need to take into account all of these workload aspects in order to actually make scheduling decisions. Now, here's a specific problem that we considered in this domain, right? And the specific problem that we're considering in this project called Themis was how do we build a fair scheduler for machine learning, right? And let's define what do we mean by fairness here, right? One of the most relevant properties for fairness that we were looking at out here was this idea of like a sharing incentive, which is that if there are n applications that are sharing a cluster, then you shouldn't be running slower than on a private cluster with 1/n the resources. So this intuitively makes sense because if I would run faster on a private cluster with smaller set of resources, I would just spend my money to buy the private cluster instead of submitting my job to the shared cluster. So I would not have an incentive to share resources with everybody else. So this is sort of the setting. So this is our goal, is to build a fair scheduler for machine learning, right? And the main questions that need to be answered are, what is sort of the interface of how do we connect these jobs to this actual execution, right? And given an interface, what is the metric that we're going to use to capture whether the sharing incentive is being satisfied or not? And then what is the mechanism that's actually going to implement logic for us to actually satisfy that requirement. So let's take a look at them one at a time. We'll start with the metric actually, right? So the metric that we came up with was that we came up with this notion of long-term finish time fairness, right? Which captures how a job's execution looks like over the course of time for when the job runs. So I'll explain that with a simple example, right? So let's say there is this green application shown in this green box out here that is submitted to this GPU cluster scheduler. Now, when it runs on the shared cluster, it has some amount of time that it takes, and it finishes at some particular time. So let's call this TSH, right? Now, if instead this user had allocated a GPU which was 1/n of the size, right, and run the same application on that smaller cluster, then you would also get a different timestamp, which is what is the independent finish time running on an independent set of GPU instances. So we'll call this TID for T independent. Now, the metric that we came up with to actually check whether there's a sharing incentive was this idea of finish time fairness, which is the ratio between these two times, which is TSH divided by TID, where TSH is the finish time of the app in the shared cluster, and TID is the finish time of the app in the exclusive cluster of a smaller size, right? And the goal with the sharing incentive is that you want for all the applications, this value rho to be less than or equal to 1. Right? Now, it's kind of interesting to see how does this finish time fairness metric relate to some of the properties that we talked about of machine learning workloads. So for example, with the locality, right? If you do get an allocation which has poor locality, that would inflate your TSH or the finish time in a shared cluster, and that could worsen the value of like rho that you have, thus leading to lack of like sharing incentive. Right. So this metric kind of captures how good an allocation that you're getting through the whole lifetime of this application. So given this metric, what is sort of the interface that we use for scheduling, right? So for designing an interface, this is where some of the key challenges came in, because we wanted an interface where you could handle a heterogeneous set of like models and hardware and so on and so forth. Right? So for example, you might have an image recognition model that you're training, while somebody else might have like an LSTM, and a third person might have like a random forest, right? And all of these are like machine learning models that are going to be trained. So it's very tricky for the cluster scheduler to be able to compute these like these finish time fairness metrics for all of these different kinds of models, or to know how their behaviors will change with different allocations given to them. So we kind of split up the role of scheduling into two halves here. So on one side, we have an agent that is going to be co-located with this application. And the agent is going to do the calculation of this like finish time fairness metric or the value of rho, and then submit it back to the scheduler. And the scheduler is then going to actually do the resource allocation given all of these finish time fairness metrics that's coming in. Right? So how is this going to work in terms of the mechanism, right? So let's take an example allocation and walk through a simple mechanism or a strawman mechanism that can be used to implement this, right? And then we'll talk about what are some issues in it and how we can overcome those issues. So the objective that the scheduler starts off with is that it wants to minimize the maximum value of rho. So it wants to minimize the maximum value of this finish time fairness metric, right? And the scheduler gets invoked whenever there are GPUs free in the cluster. So in this case, there are two GPUs which are red in color that have become available. Right? So the interface is that given these two GPUs, the scheduler asks all of these applications saying, how much do you think your finish time fairness metric will change if you were allocated these two GPUs, right? And so you could have like some applications which have a worse finish time fairness metric so far. So for example, row 1, this application which is in green, right? It might be the most unfair among all of these applications that are currently running. So one scheme could be to just sort them in decreasing order, and then we make the allocation to the one with the highest row value, right? And we make it for a particular least duration that is set out so that this application does not hog those GPUs, and we can come back and give it to some other applications later on. So this is a simple scheme, and the intuition behind the scheme is that the application which is farthest away from its like fair share needs to be given resources so that it can come closer to its fair share, right? That's the intuition behind the scheme. So now this has two problems associated with it. So one is that the allocation could be inefficient, right? So what that means is that these two GPUs, they are not actually co-located with this other set of GPUs that this green application is using, right? And so you might incur like actually a lot of like overhead in going across these servers, right? And so it might be more efficient to give it to this like blue job, which is probably like, you know, in the same server as these other two GPUs, right? The second challenge which comes here is that if you're just going to plainly sort this, then applications can lie, or they can say that, oh, I have a very high row value, right? So that in order to like hoard these GPU resources, leading again to unfair allocation, right? So these are a couple of challenges that come in with such a simple scheme. So in Themis, we introduce a couple of tweaks in order to handle these issues. The first thing that we do is that we don't look at just the job which has the highest value of row, but we look at a set of jobs which have a high value of row defined by this fraction f. So in this case, for example, I might look at the top 2 or the top 3 jobs, which are all have a very high row value, and then perform an allocation to one of those jobs. And the second thing is we actually run this auction mechanism called partial allocation auctions that incentivizes applications to actually to give us truthful values of rho, because if they do give us if they do lie about the value of like rho, then their performance will actually get affected, right? So these auction mechanisms kind of guarantee that. So just to sort of summarize how these two things help, right? So the first aspect is that we're sort of trading off sharing incentive for efficiency, right? With this fraction f that we have defined, right? Which is that if you set this fraction f to 0, right, then you have a lot of apps to allocate resources to, right? Which gives you better opportunity to place things local to where applications already have resources. And our sensitivity analysis, we did some analysis suggests that 0.8 presents a good trade-off between sharing incentive and efficiency. And secondly, we designed this like partial allocation auction, right, which incentivizes truth telling, right? So in this case, we run this like auction on all of these 1 minus f apps that are actually sort of contending for this new resource, right? And then we make allocations based on the results of the auction. Right? So more details about how the mechanism actually guarantees this is of course in the paper as well. So putting it all together, the Themis mechanism looks something like this. Every time resources become free, the scheduler offers these resources to these applications, which have very high rho values associated with them. These applications in turn make bids saying that if I get 1 extra resource, this is how my fair share metric will change. If I get 2 extra resources, this is how my fair share metric will change. And then we run the auctions in order to come up with the final allocation. I will pause at this point to take any questions.
There's a question about DRF, dominant resource fairness, as an alternative to this, or how does it kind of connect to what you're doing?
Yeah, this is a great question. For the interest of time, I skipped over a little bit of like prior work and like related work and things like that. So DRF is a dominant resource fairness is a fair sharing scheme that was kind of proposed for like MapReduce, Spark, and other applications like that. So we noticed a couple of like shortcomings of DRF when applied to this setting. So one was that giving these locality preferences, especially when you want to kind of like have things which are co-located next to each other, is something that is very hard to encode in DRF because it's looking at absolute share of resources of your bottleneck resource that you're getting, but not all resources are kind of equal in this case. Like if you think of DRF, you have like 4 CPUs, but in this case, not all the 4 CPUs are actually equally worth. Some CPUs are worth more, right? And the second main difference is DRF looks at instantaneous fairness. So it tries to make an allocation that is fair at that given point of time. And here we wanted to kind of look at long-term fairness, where we want to analyze the fairness across the entire duration of this application, because that lets us do things like take away resources from an application now and then give it more resources sometime later, right? And thereby still ensure long-term fairness while violating instantaneous fairness, right? So we believe this is a more sort of like practical metric that people might care about rather than just instantaneous fairness. Yeah.
Great. They were asking someone was asking about how rho is computed, estimated by each worker.
Oh, this is a great question, and I'm going to come back to this towards the end of the talk, right? So when you want to compute rho, you need to kind of like estimate the amount of time it's going to take for this application to run, right? We use like a simple profiling based scheme where we kind of assume we know the number of iterations that are going to be run, and we profile the time per iteration. But this is something I'll come back and talk a little bit more about at the end. Right?
Great, and I think there's more, but I think they're more like good end questions. So we'll just
okay. Sounds good. Yeah. So a quick sort of like evaluation of the scheme in Themis, right? We did this by using a trace of like machine learning jobs that were submitted, and this trace was generated using data from a Microsoft cluster that we had like profiled before. And we compared Themis to a number of other cluster schedulers for machine learning jobs like Slack, Gandiva, Theraces, and Optimus. And here we're kind of showing a CDF of the finish time fairness metric with, if you recall, we wanted one to be, all of the applications to have less than or equal to one. That was kind of our goal for incentivizing sharing, right? So Themis does kind of the best among all of the schedulers in this regard, and the maximum value, the maximum value for the finish time fairness for Themis is around 1.2. It should be noted that we don't really have admission control in this cluster, so we have to run all of the jobs that are present in the trace, right? So it's difficult to guarantee that this will always be less than equal to 1. But we did notice that the other schedulers did not take into account this placement sensitivity, this locality aspect that I was talking about. And typically that was the reason why a bunch of applications would have finish time fairness very high compared to what we were getting with Themis itself. Right? So the kind of main takeaway from this work that we did on Themis was that when we look at machine learning workloads, it's always useful to think about what is different with them and how do you sort of like design for this kind of evolving set of models and hardwares that we have. Specifically with respect to scheduling, a few differences are the need for the sharing incentive when people are using a GPU cluster, while handling things like gang scheduling, long running jobs with like these locality preferences and so on. And our approach to handle this evolving set of like models and hardware that is present in the cluster was to design this per job agent that can provide bids on the expected running time with various different configurations. Right? So this brings me to the last part of the talk, which is sort of like opportunities for symbiotic research, or another way to put it could be ML for systems for ML. Right? It becomes a little bit of a mouthful, so maybe we'll work more on coming up with a better acronym. Right? And so the reason this becomes an interesting problem is that if you notice the work that we did on the scheduling, and the question that was asked just a few minutes ago was about how does the agent come up with these bids, or how does it know, like how the performance will get impacted if you run it on more GPUs or fewer GPUs and so on. Right? So this goes back to this problem of performance prediction and quite related like performance tuning, right? Where you need some ways in order to like profile machine learning applications as well and come up with details about like how are we going to predict the performance when you give it like more hardware, or like you change the hardware kind from like a slow GPU to a fast GPU and so on and so forth, right? So performance prediction of machine learning training workloads is one of these cases where I feel these two areas intersect, because we do need some new methods to actually do that effectively, right? And they, in turn, these performance prediction methods can improve schedulers or can improve other things that are actually orchestrating and running these machine learning jobs, right? So that's one side of it. The other side, which I think becomes kind of also interesting, is that so far when I talk about performance of machine learning workloads, I'm assuming that the machine learning workload itself is fixed, right? So what do I mean by that? So what I mean is I'm assuming that some developer has specified what is the batch size, what is the learning rate, what is the quantization scheme they're using? Are they using like 32-bit floats or 16-bit floats? Are they doing compression or are they not doing compression? And that all of these are fixed. And the only thing I can change is like how many machines is this running on? So let's call this as a black box model, where black box mode, where we assume the machine learning workload is this black box, and all I can do is like run it on few machines or on more machines. That's pretty much all I can do. But on the other hand, all of these are not actually configuration knobs which are independent of like how we are actually executing this job as well. Right? So for example, if I increase my batch size, it means that I can actually do more parallel computation in a data parallel setting, right? And thus I might actually be able to use more resources effectively. Right? But if I change the batch size, it might also affect the learning rate. I might want to correspondingly change the learning rate along with batch size so that my accuracy doesn't get affected, right? So it's an open problem to consider. How are we actually going to also set these configuration knobs that are actually present as a part of ML training itself, right? And so what are these methods? Are these methods going to be guided by some other kind of like machine learning methods? Is one of the possibilities, but this is also a very interesting area for kind of like symbiotic research. And this also relates, for example, to how do you terminate these jobs? Like when do you know you're done training, and that when do you know you've picked sort of the best hyperparameters for your machine learning model, right? These are also like questions which are closely related to what I was talking about. So with that, I will conclude, right? So with this advent of like scalable and accurate machine learning methods, there's been these two areas that have sort of like been fueled by a lot of new research. One is, of course, applying machine learning to make systems better, right? Where some important considerations are the model complexity and also how do you ensure some things like reliability and explainability and so on. And I presented a short case study on database tuning and sort of showed how some of these variables like complexity and reliability need to be considered while building database tuners. And on the other hand, there's this area of like building better systems to support machine learning, where one needs to reason about new constraints or new opportunities given by machine learning workloads while trying to build something that's general in this like fast moving area. I presented a case study with like fair scheduling and how we are able to kind of like separate out the scheduler into like two parts, one to kind of like have this generality and also handle some of these constraints about locality preferences and so on. And lastly, I think there is a lot of room for doing sort of more symbiotic research across these areas going forward, right? With that, I'll take a few more questions or any other comments or clarifications people might have. Thank you.
Great. Thanks, Shiv. And now we are all virtually applauding for you. So I hope you can bask in that for a moment.
Thank you.
Yeah, it's quite something to see. So a few questions. Thanks for the talk. So I think one question maybe I could generalize a little bit. It's about just there's such a rapid change in the world. You know, machine learning seems to be changing day by day by day. For many reasons, right? There's like there's just a huge community actually, as well as just so much actual progress that's been happening. So what do you think, what kind of impact does that have on people who are working in systems, like both building systems underneath the ML world that's constantly changing, as well as trying to incorporate machine learning into the systems that they're building? Do you have some general thoughts on that?
Yeah, no, this is a great question. It is kind of challenging. So I'll first talk about the left side, this ML4 systems, right? So I think in that worldview, I actually think that a lot of the cutting edge research that's going on, we probably don't need to be on the very bleeding cutting edge, right? For models that we are incorporating into systems, right? And simple models get us a very long way, right? And so in that case, I think it's a little bit better to let the dust settle in some sense, and for the best machine learning methods to be figured out before we apply them to systems, because then we understand them better. But there are a lot of challenges on the right side. Naturally, because of the sort of the way we build systems and so on, systems is a slower moving field compared to machine learning, right? And I don't see that necessarily changing immediately, right? So I think some of the work that gets done in systems considers these things as black boxes as a result of that, because there's just too many moving parts and like too many new things that are going on that you want to take something as a black box and then say that, okay, I'm just going to assume this and then build a system around that, right? I think that approach is fair enough for a number of things. But I think what we need going forward is probably more interfaces, or like more sort of like stable ways in which we can let the machine learning people do a lot of advanced stuff while still like having a contract on how we're going to build systems, right? So these interfaces I think are coming up, but hopefully that will make things simpler. But it is hard, yeah.
Great, thanks. think a more specific question that's being asked is, it's really about performance predictability. And do you really believe that across like different GPUs that it's easy to predict? What are the challenges of predicting performance?
Yeah, it's a good question. So I think the challenges at a very high level, the machine learning models are like computation and communication, some amount of computation and some amount of communication, and then computation and communication again, right? So I think that is roughly an iteration for most machine learning models, right? And I think these, because for especially, let's say, image classification workloads and like a bunch of other sort of dense compute workloads, right? The computation is pretty predictable. So if you give it a particular dimension input, it kind of predictably takes some amount of time to compute the gradients or to do a forward pass or to do something like that, right? So that makes it a little bit more, sort of feasible to say that I have three models of GPUs, so I can kind of quickly estimate how long it's going to take by just running a few iterations, right? The communication is a little bit more tricky, but there's like kind of a few, again, common patterns because people use like all reduce or a handful of libraries to do this. So there's sort of well understood, scaling behaviors for these primitives, right? So that also makes it possible for us to predict performance. The other thing I want to say is that as with most performance prediction, the goal is not to get to the correct amount of millisecond when you're predicting this performance, right? As with, let's say, database query optimizers, the goal is to have a ranking or like have an approximate ballpark so that you're able to make informed decisions, right? So it needs to be only as accurate as it will affect the decisions that you're making in some sense. Yeah.
Great, thanks. I think there's some questions from the first part of the talks we still didn't get through, if that's okay. So
yeah, for sure.
Our knob thinking world. Did you, and Carlo already gave his thoughts, but I'm curious like what you would say, which is where, were the 5% of the knobs found to have an impact, the biggest impact, like surprising to you? Would it be surprising to some systems administrator or database administrator? Any just thoughts on like kind of what you came up with there just from that perspective?
Yeah, that's a good question. I mean, so I don't know what Carlo's take on this is. I don't know if you can read it after I'm done to get a comparison. Yes. But my take on this is that so database administrators have been remarkably successful over the past, I don't know, decades, right? Let's give it 2 or 3 decades, right? So in retrospect, it's not that surprising to me that a few knobs gets you almost most of the way, right? Which I also believe is partly because the systems are designed with that. There's like a few bottlenecks in the system that control most of the performance, right? This is also experience from like building systems and like designing systems, right? And so it's not particularly surprising to me in retrospect, I would say. But I don't know what Carlo's thoughts are. Yeah.
Carlo said a DBA is a wetware neural network that over time learns similar mental models. Automating this is important, especially for cloud environments with millions of DBs and generally in cases where ideal tuning is not just system dependent, but more broadly system and workload dependent. And then a different 5% might matter for different workloads.
Yeah, no, that's a good point as well, which is that, but I think Carlo sort of captured this idea that the DBAs are like, doing what these neural networks are kind of learning as well, right, at some level. Yeah.
Yeah.
And I think as we move to the cloud, right, we have fewer and fewer DBAs around, right? There's part of the selling story of the cloud is that there's all these already managed systems, right? That a lot of the DBA work is not there. And it's not completely true, right? I mean, part of it is, a lot of the, especially security management and et cetera, is definitely taken care of automatically. But some of these like tuning and tweaking for your workload, it's something DBA used to do. And if we provide solutions that can do it automatically, then this move to the cloud really is complete, right? Otherwise, it's somewhat partial, right? You're still missing some tuning. And again, if the tuning depends on the workload, then the same. Is not necessarily true that the same 5 rules will always be the one parameters are the one that really matters, right? They might be different one, or they might assume different values.
Right. Yeah, no, I think there's definitely the second part about what are the actual values for the parameters, right? That is something that we do need to tune, right? I mean, even with these 5 knobs, right? It's not that the default value of those 5 knobs gets us 99% of the performance, right? We took those 5 and then did a search with those 5, right? Yeah. So I think that part is definitely true as well. Yeah.
So I think we're past 5 by a bit. So let's thank the speaker again. Great job. Appreciate that you could come by and share your wisdom with us. And I guess that's it for today. We hope to see you next week. Shiv, don't hang up yet. We'll say goodbye to you more formally afterwards. And otherwise, thank you all again for joining us.
Okay. Thank you.